Our first speaker is Paul Schulte from NIOSH, the National Institute of Occupational Safety and Health. Like DTSC, NIOSH has been extremely visionary in their approach to nanotechnology as a field and really embraced this concept of prevention, for which we applaud you and are extremely grateful. So it's my delight to introduce Paul Schulte, who's the head of the Nano effort for NIOSH.
Thank you, Hillary. Thank you, Hillary. It's a real pleasure to be here. This is an exciting meeting and an exciting effort that's going on here in California. And I think the work that Dr. Nell just spoke about speaks to an approach that will help us think about how we can bring online a new technology while protecting people and the environment. And so I'm going to give you a report today on what we know about protecting workers and about the health effects of various nanomaterials to workers. I'm with the National Institute for Occupational Safety and Health. We are the federal agency that conducts research and develops guidance to protect workers. And we've been focusing on nanomaterials since the early 2000s. Workers are important to consider early on in the development of any technology because they're the first people in society who are exposed to a new technology. And certainly nanotechnology is no exception. Before we knew it, there were hundreds of products in commerce. Workers had to study the materials involved in those products and had to make those products. And so workers make and use the over 1,000 nano-enabled products that are in commerce right now. And when we talk about the workplace, it's important to think that the workplace is a broad effort of activities, a broad scale of activities that goes from the research laboratory through startup and scale-up operations, through the manufacturing and production, and then through the area which we think will be the largest ultimately, the incorporation of nanomaterials into other products, and finally all the activities involved in end-of-life of materials and products. And so it's this whole life cycle of a nanomaterial that also has its attendant workplaces and its attendant exposure scenarios. And those exposure scenarios can be different, and the control strategies and the risk projections can be different for each. So it's important to realize that we're talking about great heterogeneity in terms of workplaces. We're also talking about great heterogeneity when we talk about nanomaterials or nanoparticles. They can be a universe. There can be a universe of different types of nanomaterials based on a variety of physicochemical parameters such as size, shape, composition, solubility, crystalline structure, a whole raft of surface characteristics, as well as factors involved in the production of the material. So impurities in the production process that adhere to the nanomaterials can also be a factor. There's also features of how the nanomaterials move through air in terms of being in an aerosol, how they interact with each other, and in many cases agglomerate, and these can affect the toxicity. So all these factors are ones that can increase or decrease toxicity, as well as other attributes of nanoparticles, both scientific and commercial attributes, and attributes pertaining to how they might react in the environment. So I'm going to report to you today the status of four main steps in protecting workers. The hazard identification step, exposure assessment, risk characterization, and risk management. except I won't really say too much about exposure assessment because my colleague Mark Mettner, who will be speaking after me, will talk about exposure assessment. So I'll just introduce that and let Mark really fill that in. So first off, and let me just say that ideally it would be good with a new technology if we could go through this process sequentially. Well, we never have the ideal, and we never in occupational safety and health can go through a process sequentially. We have to do this, all these steps simultaneously, because while we're asking questions about hazard, workers are asking for guidance about how to manage perceived or potential risks. And so we don't have the luxury of going through one step at a time and then saying, aha, now here's what it means and here's what you do. Instead, we have to do all of these simultaneously. But the real engine of the activity is assessing the hazard. What do we know about the potential health effects of nanomaterials? And I guess if you harken back to the picture I showed you of all the different pictures of nanoparticles, it's important here to have a minor tutorial on the language related to nanotechnology. When we talk about nanomaterials and potential health effects of a particular nanoparticle, it's important to remember that we're relating that to a specific database, a specific toxicologic study or set of toxicologic studies. And we don't know precisely how that pertains to all the other materials in that category that might have some physicochemical parameter that's different. And so in some cases we will generalize to the whole category, but in reality we don't know specifically. And since those factors can increase or decrease toxicity, it's hard to say with full assurance that a whole category will have the effect of the index study or studies that were assessed. So that's important to keep in mind, and we'll revisit that theme because I think that is the critical issue in thinking about the health effects of nanomaterials. Now, we're not starting from scratch. We have over 100 years in the field of occupational safety and health thinking about dusts and their effects on people, particularly workers. We've looked at occupational exposures to fine and ultrafine particles in a variety of industries, and not just, and included in that are particles that are quite biologically active, such as dusts in the pharmaceutical industry. We know a lot about how you handle dusts. And just because a dust particle is smaller than what we're used to doesn't mean that it won't follow classic aerosol physics. And indeed, we're finding that most nanoparticles do follow classic aerosol, the laws of classic aerosol physics. We also have a great wealth of information, much of it derived in California and even much from this university, on the effects of air pollution, particulate air pollution, particularly the small particle component of air pollution. We also have from the fiber carcinogenesis field and the study of airborne radioactive particles, a vast amount of information on particle deposition and toxicity. So we're not starting as if this is a technology that was arrived from another planet. It follows on from the knowledge base that we have, albeit we see exciting and both scientifically and commercially exploitable properties that come with it. And but we do have an understanding of how biological organisms react to particles. So as the field started to evolve, and it really, from a commercial and worker exposure point of view, really it started evolving in the mid-90s and early 2000s. There are notable exceptions of earlier activities and earlier research, but it's a relatively new area. And hence, when you start to think about the workforce, there hasn't been a long-term exposed workforce generally. And so early on, we did some initial studies to instill particles in the lungs of animals and eventually learned how to make aerosols that the animals could breathe. And we found such findings as pulmonary fibrosis, formation of granulomas and inflammation in the lungs of animals exposed to various types of nanoparticles. We found, in some cases, lung cancer with titanium dioxide and mesothelioma-like effects. And increasingly, we're seeing a large amount of research showing cardiovascular effects, including oxidative stress responses and atherosclerotic kinds of formations. So these were the initial studies. Many of these were short-term, and they're of limited but important value. Now, I can't go through every different effect that's been shown for every type of nanoparticle, so I just made 2 slides here to just show you the range of things that have been seen with a specific type of nanomaterial. Deposition in the gas exchange regions of the lung, ability to evade phagocytosis, ability to be inhaled, go to the gas exchange region of the lung, and then enter the interstitium of the lung, producing inflammation, producing fibrosis, in some cases producing tumors and granulomas. We've seen that it can go from the gas exchange regions of the lung, and I talk about the lung primarily because that's the premier way that workers are generally exposed. Skin exposure is also of importance, and I'll mention that too, but mostly we're concerned about respiratory exposure, pulmonary exposure. So we see that various kinds of nanoparticles can enter the circulatory system, and we're concerned then what that means in terms of accessing other organ systems. We're seeing some intriguing research being done in our West Virginia lab of nanoparticles at the blood-brain barrier that induce biologic signals that have an effect in the brain, even though they don't penetrate the brain themselves. We don't know necessarily the significance of these findings, but it's part of the work we're doing. We're seeing effects on the vascular system, the microvasculature, the ability of vessels to contract and expand. We're seeing that various nanoparticles can enter cells and enter cell nuclei. The earlier work of Oberdorster on that some nanoparticles can move from the nose to the brain still gives us great concern. And we're now starting to see a growing body of evidence of skin effects, not necessarily skin absorption into the systemic system through the skin, but penetration of the epidermis of various types of nanoparticles. At first it was thought that you needed abraded skin or unhealthy skin, but we're now starting to see some data showing us that there are some types of nanoparticles that can create an inflammatory response in skin. So this is just a snapshot, and it's clearly not a comprehensive view, nor is it relate to every different type of nanoparticle, but these are the kind of effects that have been seen. Perhaps the most startling to some is the ability of, are the findings related to carbon nanotubes that have been inhaled, that have penetrated the interstitial tissues of the lung and been able to penetrate all the way through the lung to the pleural cavity. And that, coupled with some studies that have shown that nanoparticles instilled in the pleural cavity can have mesothelioma-like effects, as well as the fact that some carbon nanotubes seem to have a durability that is similar to the durability of asbestos, leads one to be quite concerned about certain types of carbon nanotubes as having a similar effect as asbestos. Now, most of the effects we see are effects that are long. We have models from other kinds of particles to show that these effects occur. But there is a new area that's a number of new areas probably, but this is one that's particularly interesting: the ability of nanoparticles to disrupt the mitotic spindle apparatus. This is the apparatus involved in cell division. and it involves the pulling apart of the chromosomes and the formation from a single cell to two daughter cells. And our colleagues in our Morgantown laboratory have conducted in vitro studies where single-walled carbon nanotubes have been added to cell cultures, lung epithelium cells specifically, and found that the nanotubes enter the nucleus and become integrated with the microtubes that are involved, that are attached to the two centromeres that are involved in the pulling apart of the cell. And in fact, they cause fragmentation of the centrosomes, the two bodies that the tubes are connected to. And in fact, they confuse the cell and they form hybrid tubes with the natural tubes that are attached to the centrosome. In fact, the dimensions of certain carbon nanotubes and the biologic tubes are similar in some ways to at about 25 nanometers. So the cell is a bit fooled. In some cases, there's disruption of the mitotic spindle and the formation and the induction of aneuploidy. We know historically that chemicals and fibers that induce this kind of damage and increase aneuploidy also increase the risk of cancer. This is sort of what it looks like. This is a normal cell. You see the two centrosomes, and that's the way it's supposed to be. They pull apart and they form a daughter cell. After exposure to a dose of single-walled carbon nanotubes, you get inappropriate kinds of formations, tripolar mitotic spindle apparatus, and in some cases four-polar. So these lead to disruption of the cell, affecting the cell reproduction, and in some cases can lead to longer-term effects, we think, including cancer. So that gives us pause, and it's an area that needs further investigation. So exposure assessment, as I said, my colleague Mark Mettner will talk mostly about this. Let me just identify 2 or 3 main points. One is there may be 1,000 nanomaterials in commerce, but we know very little about, in reality, about what kinds of exposures are occurring to workers around the world. There have been maybe 20 or 30 papers published with exposure data. A lot of it is just area data. We don't have much in the way of worker breathing zone data. We don't have much in the way of data related to specific tasks and jobs. We still have a lot of issues over what metrics to use. Historically, we've used mass per unit volume, but other metrics are important when you're talking about nanomaterials and the findings from nanotoxicology. So surface area of a given mass dose is important, particle number, particle concentration. And so we're doing studies where we investigate all of these right now and see which ones correlate with which kinds of effects. Excuse me. One of the issues in why there's such a small literature on exposure is because it's difficult to get into a lot of places where workers are handling nanomaterials. This is not employers view this information, all information pertaining to processes, as highly confidential, proprietary information, intellectual property, and hence it's difficult for them to see a way that they can share it without putting their business in jeopardy. Mark will tell you about work of our field team where we've had gracious and highly responsible employers who wanted to work with us and use their facilities as laboratories, so we've appreciated that. Clearly, though, we're only getting a view of a volunteer population. We don't really know what the rural world is doing. Also, we've yet to assess a wide range of operations or a wide range of particles. I had another slide that showed all the categories of commercial nanomaterials and a little blip showing the fraction that we've looked at. So we still have a long, long, long way to go. And we don't have much about downstream users. Laboratory, manufacturer, production, and then the people who work beyond in production and beyond, who apply kinetic energy in the form of sawing, cutting, drilling, do they release free nanoparticles from nanoparticles that are embedded in a matrix? I had initially thought I wouldn't think so, but I'm starting to see data being generated. Mark may talk about some. Here's the August issue of the Journal Annuals of Occupational Hygiene. The cover story, nanoparticles from sanding. It's a simulation study, but it does show the generation of free nanoparticles in people who sand coatings that have nanomaterials in them. Moving on, you can have a hazard, but if you don't have exposure to it, you don't have any risk. And so you need to put hazard and exposure together and then be able to make some statement, some assessment of what the actual risk, the probability of a negative effect occurring. And so we have a whole process of risk characterization. Usually we can think of it in terms of sort of what kind of toxicity data do we have? And if we have adequate data, we can do a quantitative risk assessment and then maybe even determine an occupational exposure limit. Often we will only have suggestive or insufficient data, and here we would need more qualitative approaches to assess the data and more qualitative approaches to base our guidance. I think the exciting work that Dr. Nell pointed out may help us modify or clarify this kind of framework if we start to be able to screen large numbers of nanomaterials and then relate them to the kinds of outcomes that he was showing. And so I think this picture will change, but it's a general framework. And I want to talk first about quantitative risk assessment. And this is an area of great importance in occupational safety and health. We have long used animal models to predict the potential risks to workers. And it's clear that this will also work in involving nanomaterials. And essentially what we do is that we take a toxicologic study, exposure of a laboratory animal, often a rat. We assess what the dose-response relationship is and determine what the dose to a particular organ is that relates to a particular level of risk. And then we make the assumption that we will see an equal response to equivalent dose in humans, and then we work up the other side, figuring out over a working lifetime what kinds of doses a worker will get, and then we can make a decision on where we want to set a standard. And so this is what we've been doing for a number of substances, many of which are not nanomaterials, but recently we have two examples of approaches with nanomaterials. First involves titanium dioxide, and we looked at both nanoscale or ultrafine titanium dioxide and fine-size titanium dioxide. And we actually conducted the risk assessment using as the metric of dose surface area per unit volume. But we thought that if we made a recommended exposure limit in terms of surface area, that this would be impractical for the present-day practice of workplace control. So we back-calculated it to mass. This is an evolving area and will certainly be one that needs further thinking. But the point is that, if you take titanium dioxide and look at the dose-response relationship by surface area, both the larger particles, the particles greater than 100 nanometers, and the smaller particles, those less than 100 nanometers, more or less fall out on the same curve, clearly separated, but they do fall out on the same curve. And so you can essentially assess the risks on that curve, but you'll need a lot more. You'll get a lot more surface area with the smaller size particles, and hence, because of that, the risk for inflammation and possibly tumor development will be greater for the fine size, for an equal mass of fine size titanium dioxide versus, or of ultrafine size titanium dioxide versus fine size. And so we have recommended 2 levels to control exposure, about a 10-fold or 15-fold difference in the 2 levels, this lower level being for the nanoscale or ultrafine titanium dioxide. And the key message here is that we have many substances that have occupational exposure limits, but they're limits for essentially the bulk or larger size particle, and these will not be relevant in the for nanomaterials. And indeed, since most of the periodic chart can essentially be nano-sized, we have a lot of work ahead of us to identify exposure limits. Similarly, we did the same thing for carbon nanotubes. We used a data set involving rats exposed to 3 doses. Here the endpoint was pulmonary fibrosis, and we were looking at setting a level, an occupational exposure limit that would keep risks at less than 1 in 1,000 over a working lifetime. We found that to do that, the exposure limit had to be low, and as we started to proceed to look at what it would take for a lower limit, we passed the limit of quantitation. So so the best we can recommend at this point is the limit of quantitation, which is 7 micrograms per cubic meter. This is still provisional, and we'll be probably putting this out for public comment in the near future. But it does show that, and even at that level, there is probably some residual risk. And so we're concerned about what the appropriate limit will be. But we think that this will be highly protective. And then, and again, this is in terms of mass per unit volume. If you think that carbon nanotubes have some similarity to asbestos, you might say, well, why don't you use the same approach you use with asbestos, which is fiber counting, number of fibers per unit volume of air. And indeed, when you see some of the micrographs, I think that Mark will show, you'll see that it's not easy to count nanofibers, especially carbon nanofibers, because you're looking at more of a bird's nest than you are discrete fibers like you see with asbestos. And so we haven't got to the point where we figured out how to make a good guidance for counting rules. So we're using mass per unit volume. The last area, you can characterize the risk, but you still have to figure out what you do with all this information. How do you manage the risk? Well, there are 4 points that I'd like to stress. One is the importance of following the hierarchy of controls, but that's couched within a larger framework, and that is that nanomaterials are like other substances in the workplace. They should be part of a of a risk management program, a hazard assessment and risk management program. And they are not necessarily unique in that regard. And so all the elements that pertain to an overall company health and safety program should pertain to those parts of the operations that involve nanomaterials. And clearly when we get into looking at the controls related to nanomaterials, we strongly recommend following the hierarchy of controls, which first and foremost involves elimination, substitution, isolation, and engineering controls. Now clearly in some cases eliminating the nanomaterial might not be possible, since that's the product of the technology and being developed. So but there may be ways to design the nanomaterial to mitigate the toxicity, and I'll talk about that in a second. Let me just say though, as far as following the hierarchy of controls, we have a lot of evidence that shows that controls work for nanomaterials, at least in some of the kinds of operations that we've looked at, and clearly they can be scaled up to cover high volume operations. And indeed, we have data that shows, such as in this study, which involves clean out of a reactor using where the air is controlled using local exhaust ventilation, and you can see, based in terms of particle counts and in terms of mass, quite a large reduction of the number of particles or the mass of particles. And here's just amplifies that point, data showing what happens when the exhaust is on and when the exhaust is not. You see from 74 to 96% reduction of particles. We believe that nanoparticles follow the classic rules of aerosol physics, and so that's a critical point. Similarly, we have data that show that classic personal protective equipment such as the N95 work. Here you can see in this slide that the very small particles clearly don't penetrate an N95, and even the most penetrating diameters, which is around 50 or 60 nanometers, are stopped in 98% of the time. All of these control data have some validation to them, but they need further research. We need to know what the limits of those controls are, what factors might mitigate control. But this is at least a good foundation. I'm running out of time, so let me just say that from a regulatory point of view, there aren't any officially promulgated occupational exposure limits specifically for nanomaterials, but there are a number that have been proposed as unofficial or benchmark ones. We think this is important. I'm going to skip that, and let me just say that the last item that I want to mention is that it's critical to think about the point that was made initially, that how can we sustain this technology in a way that both protects workers and allows us to benefit from it. And one way is to think of design strategies for the nanomaterials that will mitigate the toxic effects where they exist. And so we're planning a conference for 2011 where we'll talk about prevention through design in terms of designing the molecule and designing the process. The last thing I want to talk about is, where are we going? Well, where we're going is we as a society have proffered the concept that there's a need for precautionary approaches, but we need to assess to what extent those precautions are taking place. We need to conduct then efforts to establish exposure registries and develop epidemiologic studies to assess to what extent those measures have been effective. And so I think that is the next step in the effort, and if there are questions about that, I'll discuss them then. So with that, I think I'll stop, and I have a few more just to say that this is where we've been coming from, the idea that when you have a lower degree of certainty, you need a higher degree of caution. And it's our job to fill in, to move down in the certainty pyramid so we're more certain, and so that our degree of caution can be commensurate with our certainty. But I think all in all, we've made a good start, we as a community, in thinking about the health effects related to nanomaterials, and more than that, honoring those concerns and trying to take action to address them. So thank you very much.
One or two questions? Oh, great. Okay, good. Okay. So this is a question from online. We could have you read it.
Are the 16 proposed OEL NIOSH RELs or industry/consensus OELs? Yes, I was not clear. Those are recommended exposure limits from a variety of organizations. They're not, one of them is a NIOSH one, but they're from a variety of different organizations around the world.
Any questions from the audience? Just raise your hand and we'll bring her up around the microphone.
Is a gas mask the only way to protect workers?
No, and in fact it's the least desirable way. The best way to protect workers is to either modify the material or develop engineering controls that involve various kinds of ventilation. If you can't do those, those kinds of controls, in some cases, a dust mask will be usable.
Okay, if you don't mind, another quick question.
Sure.
Those sunscreens that contain nano titanium dioxide or nano zinc oxide, will they go through the skin?
I'm not knowledgeable about sunscreen, so I can't really tell you that.
Thank you. The local exhaust ventilation that you were using, what was it terminating in? Was it a typical bag house, or was it HEPA filtration? Was it particulate deposition, or did you have electrostatic precipitator? What was at the end point of your local exhaust? And did you take any measurements in the area around the end point of the local exhaust?
Mark, are you going to be covering some of that?
Okay,
if I could defer that to my colleague, that would be better. Thank you.
Is there one place to get all of the 16 proposed OELs?
In fact, there is in a paper that we recently published in the Journal of Nanoparticle Research. We have a table that lists all of those. It's Schulte et al. And if you talk to me at the break, I can get your email address and send it to you.
Oh, great. Is it on the NIOSH website?
It's referred to.
Referred to?
It's not actually posted there. And in fact, if you want a lot of this information, it's in materials that are on the NIOSH website.
So, do you have any data on disposable masks? Protection offered by disposable masks rather than the N95 filter?
I don't think so. I mean, we see the N95 as of limited use and in a sense disposable, but we don't have. I don't think we have data on anything less. I think I have seen data on such things as surgical masks or other kinds of short-term use respirators, but I don't think that they showed that they were very effective for these nanoparticles. But I don't know. Maybe Mark will allude to that in his discussion. Sorry.
Dr. Schulte, there's a question from the web as well. It says, I'm planning to establish work practices. You mentioned confidentiality of information as a predicament. How do you overcome this?
Well, that shouldn't affect establishing appropriate work practices. I mean, I think, well, for a company to function, they have to keep some of their information confidential from competitors, but there's a certain transparency they need to have with their workers in terms of their right to know what hazards or potential hazards they're dealing with. So in terms of risk communication and right to know of employees in a company, that shouldn't be a barrier to employers sharing information to a point that they can establish the appropriate risk work practices.
So we have one more minute, so one last question for Professor Schulte.
There's another question from the web if no one in the room. Are there studies about mixtures of nano-sized particles and nanomaterials?
Yes and no. Some of the studies of carbon nanotubes are inherent mixtures because they contain both the carbon nanotubes and some of the metal catalyst, which is essentially an impurity. So in that sense, it's a mixture. I don't know of any intentionally developed animal tox studies where they took different types of nanoparticles and mixed them together and then exposed animals. I could see a place for that at some point. And then clearly, when we go into workplaces, and Mark will talk about this, while we're looking for a specifically engineered nanoparticle, we have to be cognizant of the fact that there are incidental nanoparticles that come off all kinds of things that are in the workplace that can influence our readings and measurements. So in that sense, in the real world situations, they're mixtures to face.